You having fun? I thank you for those. We will. Yes, bigger the better. Yeah, I know it's one of those things. All right. Apparently, none of these speakers work except for the one in the middle.
Hello, Tess.
At least I'm not talking out of the projector, right? Maximum gain before except for there's a delay. If there's a delay, that changes things. But if it's a constantly changing delay, no feedback there. Hello, everyone. Thank you for being here for this presentation. Thank you, Dr. Floyd Toole, for coming to this event. I got some new faces, some old faces. By that I mean people who've been here before. We are the Toronto Audio Engineering Society. We very much try to bring the community together for events such as this to disseminate information about this technology, technologies in general, and hope to educate and hope to entertain all at the same time. I'd like to thank our sponsors. Some of them are here. Let's take a look. I have it here somewhere. Gear Audio, Sonotechnique, avshop.ca. I don't think they renewed, so we'll have to bug them. Adamson, Lawo, Solotech, I think Solotech, yeah. Toronto Metropolitan University. Big round of applause for Finley. Of course, the University of Toronto is also one of the pillars of our community, and the music department, Faculty of Music at University of Toronto is very important to us. So it's we're very yes. Thank you for perpetuating this. It's a great thing. Before we get started, Dr. Toole, here I got the 4th edition. If you could,
in hardcover.
I got the hardcover. My wife was really upset that I spent more than $200 on a book.
I'm impressed.
Yeah, he's impressed. The guy who wrote it's impressed that I paid the mony for that.
I haven't seen a hard copy yet.
No.
But,
first one in Canada. So first one to get signed too. If
okay.
So it's extra value.
I'll sign it, Anthony.
Thank you. Yeah, keep it up there. Make sure nobody steals that one because that.
Okay.
Yeah, it's a hard thing to tell your wife you're spending $200 on a book. Highly recognized for his work and globally esteemed for his outstanding contributions to both audio engineering and consumer technology world. Okay, all right. Dr. Floyd Toole is here. I'm going to give as much time as we can to him so he can speak as much as possible. Let's try to keep our questions to the minimum. We're going to have a little break in the middle. I've kind of just said I'm going to pull the cord on his back and let him go.
Well, I kind of verbalized this talk this morning in the hotel room, and I think there's a natural break about 45, 50 minutes in, so we'll have a bio break at that point. Good evening. It's an honor and a pleasure to be here amongst you. It really is. I'm Floyd Toole, not Doctor. The doctor bit sounds a bit pretentious, actually. It's real, but That's not me. I put this little provocative note on the opening slide just there to plant the seed of what's to come, because we need neutral loudspeakers. Why do we need neutral loudspeakers? Because we have neutral everything else in the audio chain, electronics and so on. I started life as an electronics engineer. I was going to be a transistor circuit designer, and we design an amplifier. It's going to have a flat frequency response. It's just automatic. I mean, you do it because that's what it should be. You get to a loudspeaker. Well, I didn't have any experience with loudspeaker measurements until I joined NRC, but I'll tell you about that in a few seconds, because we've got to face the fact that audio is really a very complicated topic. We have art and science. These are the C.P. Snow two cultures, the humanities and science, that really have trouble communicating viably with each other. It's true in audio to some extent. While art and opinions have a very strong, solid connection, science and facts have a strong, solid connection. Art and science, it's kind of hazy there. Opinions might be useful as facts if we can find a way to get reliable, trustworthy, repeatable opinions from large populations of people. Then they kind of statistically resemble facts. The problem is that opinions drive our industry. They pretty much determine what's made, because I don't think any companies would design and build a loudspeaker, determine what loudspeakers end up on the market. And they certainly determine what ends up in our homes and in our workplaces if we're using loudspeakers, because we listen, right? Measurements have a problem too. Opinions are influenced by factors that aren't related to the sound. What we see, what we know about the product we're listening to, already has biased our minds in a certain direction before even the first note of music is struck. Facts are another problem, because we can measure all kinds of things, yet some of them really matter to what we're interrogating, what perception we're looking at. And others are really only marginally or almost not at all influential in that particular perception. So we have to identify what measurements are relevant and how we interpret them, numerically or graphically. So in the end, really, and this is really an industry problem, industry from the consumer side and industry from the professional audio side. How do you separate the art from the technology that is used to create that art in the studios and to reproduce that art in our homes? I mean, there are so many people I talked to over the years who they love their loudspeakers, or they love their amplifier, or they love their wire even. I mean, there are even crazy people like that, but they exist. Audio jewelry is a big business. It has nothing to do with sound. It has everything to do with image. So here's that provocative statement that you were introduced to at the beginning. Liking the loudspeaker is the answer to the wrong question. So how do we determine how do we find a neutral loudspeaker if we decide we want one? We don't listen to measurements, we listen to sounds, and from that we form opinions, and this is where the fundamental problems begin, because when we listen to these sounds, we're listening to input from people here, the musicians themselves and the recording and mastering engineers who have 2 ears and brains and opinions. And here we get through a loudspeaker, and there's our transducer designers and systems designers and cabinet designers, and all under management and all for a profit motive, and opinions get involved there. A room, my goodness, we all have rooms, whether they're professional rooms or home rooms, domestic rooms, and they're all different from one another, and they are part of what we hear. You can't escape them. As long as we want to keep the rain and the wind out, we have a room. Those factors certainly affect our opinions, but then there's this subtle thing, not so subtle thing, of what we see with our eyes and what we know in our minds about whatever we're listening to. Those are all biasing influences, and so out of that multitude of biasing influences come opinions, and they are not simple perceptions. Fortunately, in 1965, when I began my research at NRC, I didn't know anything about this. Otherwise, I might have had second thoughts. In 1965, I didn't know anything about loudspeakers. But looking back on it, there were certain facts and there was folklore. All loudspeakers had personalities in 1965. Cast your minds back, those who can. It was believed that you had to find a loudspeaker that matched your tastes and your preferences. It was a personal choice because they were all different. It was believed that we couldn't measure what we could hear because the manufacturer's specifications didn't seem to translate into what I heard, and therefore measurements are meaningless. And that's sadly pretty much the case today. There are some manufacturers out there who actually publish useful information, but most don't. And so subjective opinions drove the audio industry. They drove the products that went to market, and they drove the products that went to homes and into professional recording studios. Just for your perspective, those are the measurements that I made on those first loudspeakers in 1965. And there's a tannoy there, there's a quad electrostatic there's a KEF Concord, there's an acoustic research AR3 that's in the Smithsonian Museum. It warrants that. There's the Wharfdales, that's the AR, there's the tannoy, there's the quad, there's the KEF and a Wharfdale. All respected names. Even then, they were very respected names, and some of them still are. But that's what I wanted to see in my naivete. That's what I was looking for, and I didn't get it. So this was interesting. My first reaction was, good God, can they sound as bad as they look? Because these were consumer products, expensive consumer products that people shopped for carefully, thoughtfully, purchased, lived with at home, enjoyed music through, I'm sure. And yet, they can't be neutral. So my Friday afternoon experiment, at NRC, we scientists had a habit of doing, on a Friday afternoon, if we had a brainwave, we'd get a bunch of people together and get a bunch of our colleagues together and just throw the ideas around and see what happened. And this time I decided I'd get a few of my colleagues in and we'd listen to loudspeakers. And having a little bit of a scientific background by that time, I designed an experiment. It was blind because I knew people would be biased by what they knew or saw, even then. I made them equally loud because we were not testing sensitivity or efficiency, and the louder speaker would have a benefit just simply because it was louder. It would attract attention to itself. And I played a bunch of music, some classical, some popular, choral, symphonic, what have you. Quite a selection. And during each of these musical selections, the sound would be switched randomly from one speaker to another. There were 4 at a time behind this screen. And people were asked to just write their comments, and at the end of the exercise of each session, to write a score on a scale of 10. 0 is rubbish, 10 is perfection. Where does each of those particular loudspeakers stand on that scale of 0 to 10? And they did it. They didn't even find it terribly difficult. And the results were, well, they did sound as bad as they looked, and they were very different from one another. When you hear them side by side, my goodness, they were as different as chalk and cheese. But amazingly, and this amazed all of us, there was general agreement among the listeners about which ones were preferred. Where were these personal preferences that we were led to believe were the reality of the time? And some listeners who brought their own products disliked their own loudspeakers. They had purchased them, paid money, and lived with them and enjoyed them for sometimes up to a couple of years, I remember. And yet when they heard them compared to something else behind a screen, they didn't like them at all. That was very disturbing for them. Had they adapted to the faults in those loudspeakers while they lived with them? Is adaptation a factor in our forming of opinions? The answer is yes, of course, because humans adapt to all manner of things. Temperature, brightness, what have you. The loudspeaker that received the highest average rating was the one with the best looking measurements. Could it be possible that we can measure what we hear? I mean, this is the number one experiment in my lifetime. And the measurements were anechoic, not room curves. So is it possible that binaural hearing, this binaural hearing that I was at the time investigating, is it possible that binaural hearing allows us to separate the source of the sound from the environment in which it's reproducing or producing, whether it's can be producing or reproducing? And the answer is possibly yes. That's a lot of information from the very first experiment. And we did more and found that adaptation is definitely a factor, because time and time again people would bring their own loudspeakers in for evaluation and go away wishing they hadn't bought them. So adaptation is a real phenomenon. So if you work with something, live with something, you will be adapting to its peculiarities if it has them. And the experimental method is clearly a factor, because we have to set up a situation where, any experiment has to have you minimize the irrelevant variables, and the room would be an irrelevant variable in this case, and the program would be an irrelevant variable, because we wanted to judge the differences between the loudspeakers. And in this particular case, that's exactly what happened. By the greatest of good fortune, not forethought at all, I chose the multiple loudspeaker method, and the room and the program during the comparisons were relatively constant factors. Now, the listeners could not possibly know what the original recordings sounded like. They weren't there at the final mix or mastering experience. They weren't at the concert, which was captured in live performance. But they commented frequently and candidly, most candidly sometimes, about the aspects of sounds that they did not like. They might have had trouble recognizing what was good, but they had no trouble at all describing what was terrible in very blunt terms. It was lovely. I still have those sheets. They're great. In other words, the best loudspeaker in the test was the one with the fewest audible flaws. You take away the flaws, and it gets better. Interesting. The comments about the good speakers, well, this sounds good, that's all. And that goes on to this day. The comments on good loudspeakers are, yeah, it sounds great to me. Bad loudspeakers, people will write a page of detailed comment about how terrible it is in 10,000 different ways. Anyway, what defects were they responding to? Well, there was a relationship, it seemed, between the anechoic frequency response curves and what they were listening to and preferred. So the anechoic curves obviously contained some of the clues. Measurements were needed, for sure, but only trustworthy opinions can show the way. So we need science, and science means, in this case, subjective measurements, unbiased, repeatable opinions. I have to find a way to do that. And technical measurements, revealing measurements that relate to the loudspeakers and to the rooms through which the loudspeakers communicate. And in the end, we're going to try to tie it all together with some kind of psychoacoustic relationships. And how we listen determines the opinions we get. The most common listening method is the primitive, it's in experimental psychology, it's called the single stimulus method. You take it home and listen to it, or you spend time with a product anywhere, on the job or at home. And if that's the experience, then there are no instant comparisons to other loudspeakers. The auditory memory, in spite of what we think about it, is really relatively short and imprecise at that. Our recollections of prior experiences with other products and with the live sounds are not very reliable. This has been tested many times. Timbral signatures of recordings in rooms are combined with the loudspeaker timbres, so it's the combination that you're listening to. You're listening to a package of loudspeaker, room, and recording. And that's what you're listening to. And so if you do a sighted test in a familiar room, your home, for example, it's substantially a record review. If you read subjective reviewers' reviews, and they go pages and pages and pages, they're elaborate record reviews. They can't separate what's in the record from what's in the loudspeaker because they don't have comparisons. Over time, the listener adapts. He normalizes to whatever sound there is, to some extent. I suppose if the product has such a dreadful mistake, then or error or flaw, then you can't normalize it. But most you can normalize to some extent. But sometimes the sound is initially displeasing, but you persist, and over time it gets to be more acceptable. And this is obviously often attributed to the product breaking in. And there is this breaking in myth in the audio industry. Components that break in, if you think about it, always improve with time. They never get worse. Why is that? How could that possibly be? Statistically, some of them have to get worse with time, but no, they always get better. Well, they always get better. Well, that's interesting. Okay. Loudspeakers are designed not to change. I've been around a lot of loudspeaker designers in my lifetime. Not one of them designs a speaker that will deteriorate with time or get better with time. Otherwise, loudspeakers would have vintages like wine. You can imagine the commercial, the ads on the internet for selling a 10-year-old speaker broken in, nothing louder, nothing more violent than the Beatles ever played on it. That kind of. So only woofers and subwoofers may change very slightly, where the diaphragms move over large distances and the suspensions loosen up, and they change. We can measure the change. It's pretty small as a rule. And subjectively, it's often completely lost in the confusion of resonance, room resonances. It's not serious, it's small. It has been tested many times. However, in the loudspeaker reviewing side of the industry, it's totally different. Here are two loudspeakers that were reviewed by a very experienced reviewer. He has his own YouTube channel even now, right at this moment. And he listened to the loudspeaker on the left, and he loved it right out of the box. He had no problem at all. This is a rave review from the very first moment of listening to it. The second one, he wasn't too sure about. But he had, as he admitted in the first paragraph of the review, he had a passion for electrostatic loudspeakers. And this was an electrostatic loudspeaker. And so the fact that it displeased him slightly didn't deter him from carrying on, and he wrote a detailed exposition of how it gradually became better sounding, and after about 30 days he thought it finally revealed its true self. Now, what do you think? Do you suppose the loudspeaker acquired musical abilities over those 30 days, or was he just putting up with the crap that he was listening to? Both loudspeakers got rave reviews. This was in Stereophile magazine, and John Atkinson does measurements, and their measurements are adequately good. And he looked at those measurements, and even he questioned his measurements. The reviewer thought, nah, that's okay. Give it a rave review. It's as good as speakers get. Sure. Okay, second kind of comparison is where you do a second speaker evaluation technique is to do a comparison. And the simplest of all comparisons is A and B. And of course, that's a good step in the right direction because the program is constant, the room is constant, and you're comparing A and B loudspeakers. The loudspeaker is the variable. However, if that's all you do, then you may not be aware that in such comparisons, you may not be aware, you don't pay attention to the factors that are common in the two sounds. And this is a reason never to use the same loudspeaker as a reference when you're doing shopping or comparisons, because a flaw in the reference then becomes an advantage, right? And the only way you've got to break that circle. The only way to break that circle is to get out of the subjective and get into the objective, get into the measurements. Then you can see what you're listening to. But the problem, some manufacturers get into this trap, and even Consumer Reports got into the trap. They used AR3s as their reference for several years, and of course the AR products did very, very well for a period of time because they sounded like the reference, they had the same problems. Anyway, to be useful, several A-B comparisons have to be done. You have to pull in a population of products and mix them up in pairs, and To do that statistically significantly is very time consuming and labor intensive, so you don't do it. Instead, you do the multiple loudspeaker test. It is the most revealing method, it is the most efficient method, and by the greatest of good luck, it was the one I was fortunate enough to choose for my first experiment. In it, you compare 3 or 4 equally loud loudspeakers in random sequence or in a personally chosen sequence if you're listening alone. The loudspeaker is the variable, the program is constant, the room is constant if positional substitution is employed. Otherwise, the speakers will be in different positions in the room, and you know that different position loudspeakers, the same loudspeaker in different positions will activate room modes in a different way. So if they're in different locations and you're comparing one with the other, then you have to randomize the comparisons, do the tests over and over again. And I did this when I was back at NRC, and it was ridiculously time consuming, but it had to be done, and it makes a difference. If positional that's what I just said there. If you don't use positional substitution, you have to randomize positions. And the data can be statistically analyzed, and it has very high statistical power. That is to say, if there's a difference to be found, this technique will probably find it. Here's the technique I used in 1985 for positional substitution at NRC. It's just little turntables, 4 feet diameter. They were rotated by hand. We had human labor behind the screen changing the positions. Now they're all motorized, they're computer controlled, and you can buy them off the shelf or if you want to pay a lot of money, or you can build them yourself. And some online do-it-yourselfers have actually built computerized rotatable position changing systems and done really valid little tests on small loudspeakers. At Harman, we had a larger budget and higher objectives. We wanted to test stereo pairs as well as single loudspeakers, and we wanted to have left, center, right capabilities as well as just left and right. And so we built this elaborate pneumatically driven platform. The whole platform moves left to right, and these little mini platforms move forward and back. They bring the loudspeakers into the listening position. And now you can choose to have stereo pairs or a left, center, right, and compare 1, 2, 3 pairs of speakers, or up to 4 single speakers. And you can decide where they go. You can listen. They can all be compared at that location or that location or that location, or you can just choose it. It's all free choice, and that was nice. It's $200,000. You can do it. It's a big deal. And the listeners come in one at a time. We sometimes use small groups, but groups are a problem because almost inevitably somebody in the group is going to have a strong opinion, and they're going to make it clear that they have a strong opinion. And once that happens, then everybody else kind of gets biased in that direction. So we prefer to do single listener tests. And in that case, you sit down with a laptop and or just a pad loudspeaker, a pad computer. And you select the loudspeakers by number. The number codes are changed when the music changes. So for each selection of music, the number codes hold. But when the music changes, the number codes are randomized. So each piece of music starts a whole new experiment. You don't know which loudspeaker you're listening to. And the music consists of 30-second repeated loops, segued very tastefully so that it's not objectionable. You can hear exactly the same passage of music through every loudspeaker. It's not like turning on a symphony and listening to the crescendos and diminuendos, and you can't hear the same sound through each loudspeaker. So we destroy the music to get a good test signal, and there's no time limit, so nobody's rushed. And this is what it looked like behind the screen. It's all computer controlled. The computer decides everything about the experiment and stores away the data and computes the statistics and so on. And a video camera up there in the corner prevents people from cheating, because it might be tempted to peek behind the screen. Anyway, tests have been performed on hundreds of loudspeakers. I'm not exaggerating. Hundreds of loudspeakers with hundreds of listeners. And as a result, we have and still have an enormous database of minimally biased subjective ratings, which is a part of the science database that we need to have. The regular listeners were selected for their hearing ability. The thresholds have to be within 15 to 20 dB of audiometric zero. In that case, they represent not a select population, but about 75% of the population in general. So we're not being selective, but we do reject people who have hearing loss. Those who pass that test are trained to hear resonances. Sean Olive made up a little online training program where they could listen to sounds colored by resonances of different frequencies and cues. And people got very good at identifying what frequency the resonance was at and what cue it might have there, because this is information that the engineers who design the loudspeakers need to have. They want to know what the problems are so that they can take the speaker back into the lab and fix it. So the opinions were very consistent, and they came quickly from these people. More importantly, they agreed with the ratings of the listeners from all other backgrounds. So listeners who don't have the training and the experience still have opinions, but their opinions might vary from time to time because we present the same sounds over and over again. Whereas the trained listeners will give you much more consistent answers, but fortunately when they average even the large variability answers, they agree with the ratings of these trained listeners. Hearing, we test in mono, but we listen in stereo. And surely the extra complexities of the stereo sound stage, imaging and development must require higher performance than mono, but it's not the case. Here's a test that I did in 1985. And we did it in mono and we did it in stereo. And in the mono test, interestingly enough, people heard stereo qualities, just with the single loudspeaker. They had opinions about spaciousness. Most of the comments they gave us indicated that it had something to do with the loudspeaker disappearing behind the screen. That the better quality loudspeakers didn't draw attention to themselves. But certain loudspeakers you could shoot a hole in the tweeter without looking at it. In this case, we had two Conan domes, a two-way system, a three-way system, and the quad electrostatic. And the quad didn't do terribly well in the sound quality, but we asked them a separate set of questions about spatial quality, and the quad again did not do well. Interesting that the trend is the same for space and sound quality. Maybe people can't separate the two, who knows. But you do it in stereo, and you get a whole bunch of different answers. First of all, the differences that were very striking here aren't striking there. Maybe there's a hint of it here. Maybe that's a slightly compressed version of that. But the spatial quality, it's all over the map. And the reason why is when we go back and look at the answers people gave for different recorded selections, the recording determines most of the spatial qualities, not the playback apparatus. And that was alone interesting, except for recordings that had hard panned, close mic'd sounds like the pop music of that period. And you have that kind of recording, and the hard panned left and right images are in fact mono sounds. And so for those components of the stereo sound stage, people were making in effect monophonic judgments, and they gave the same ratings for the popular music selection as they gave in the mono selection. Interesting. So how we do the test makes a difference, and what we're listening to makes a difference. So why is this happening? Why would we be less sensitive to differences in stereo than we are in mono? It took a while to figure this one out. Reflections in rooms increase our sensitivity to resonances. Sean and I did elaborate threshold detection tests on resonances, and we did them in the anechoic chamber to begin with. We did them through headphones. We did them in ordinary rooms, and we did them in very reverberant rooms. And the threshold goes down as the reflections increase, because every reflection is a repetition of the direct sound, and it gives us another look at the sound. It gives us more opportunities to judge what's in that sound in the details respect. This is well known in experimental psychology as well, and that's why I use the word looks, because that's the term they use. More looks, when you hear things over and over and over again, you get more sensitive to various aspects of the sound you're hearing. This happens in concerts, in live performances. I mean, if you've ever heard a live concert in the park, it's most disappointing. The musicians are playing well, their instruments are good instruments, but they don't sound very good. You pray for rain so that they have to move the concert indoors to any room, and then suddenly it has richness, it's timbral richness. And if you're doing a recording, you're going to add a little reverb, because when you add that reverb, it adds a little sweetness to the mix, it adds richness. And the richness is because you're giving the two ears in the brain more opportunities to hear the direct sound. So what it means is that in listening rooms, loudspeaker resonance are more audible. And that's not good. So the rooms allow us to hear more timbral details in the music, but we also hear this problems more audibly in the loudspeakers. However, recordings contain what I call large space envelopment. Nobody in a recording studio would dial in synthesized reverberation appropriate to a room the size of your listening room. You're always going to use a big room. When you do a recording of a symphony orchestra, you want to convey the concert hall illusion, not the listening room illusion. The concert hall illusion, the big space illusion, is superimposed on the small space illusion. It's the small space illusion, though, that contains the information about the loudspeaker resonances, but perceptually we are more attracted to the large space illusion, and so the small space illusion tends to be disappeared. If we do the tests with technical signals like pink noise and clicks, there is no difference between stereo and mono. However, if you have mono music and stereo music, there's a huge difference. And it's the large space reflected sound cues that are in the stereo recordings. Now, if it's the large space envelopment that's attracting us away from hearing these resonances, multi-channel should be even worse, or better, one or the other, because multi-channel delivers the illusion of space much better than stereo does. You can dial it in to whatever extent you want, and it should be even more distracting than stereo, except for hard panned signals, because all recordings will have some hard panned sounds, and in movies we have the center channel, which is a mono signal conveying most of the on-screen sounds. And for those particular components of the stereo or the multi-channel mixes, the resonances are revealed. And here's a good test. This is mono versus stereo versus multi-channel. 3 loudspeakers, one pretty bad, one fair, and one pretty good. And the pretty good loudspeaker won all 3 tests. The pretty bad loudspeaker got better as you added the stereo channel count. And the middle one was more noticeable. The difference between the two better loudspeakers was more noticeable when the overall range was reduced. When this bad loudspeaker existed, everything else sounded really good by comparison. When that sounded a little better, you could hear a difference between these two. But when these two were really, when this sounded quite good, then we heard a real difference between the two. This is subjective scaling. Subjective scales are elastic. And that's one of the things you'll have to do to pay attention to. In an A-B comparison, you'll tend to get large differences. You know, this speaker blew away that speaker. Well, rubbish. If you added C and it was down here, maybe the A and B would be quite close to each other. So subjective scaling is a study in itself. So, if we want to subjectively identify timbrally neutral loudspeakers, how are we going to do this? Well, we're going to listen blind, and we're going to listen in mono. We're going to compare 3 or 4 loudspeakers at a time, loudness equalized, and we're going to use positional substitution to eliminate the room as a variable, or if we can't do that, then we're going to have to randomize the locations, and this is important to do. And we're going to listen to recordings that reveal resonances, and some are definitely better than others. I call it, there are some recordings that I would choose to demonstrate a bad loudspeaker and convince an audience that it sounds good. And there are other recordings that I would use to reveal the real differences between the loudspeakers. And the real ones that reveal the real differences are those in general that have broad bandwidth, especially down to the low end of the frequency range, and high spectral density, which is to say some significant orchestration, and reverberation to add repetitions. After identifying the neutral loudspeakers, take them home or wherever and enjoy them in stereo and multi-channel. So here's a summary. The multiple loudspeaker method is the best, but it's expensive and it's time consuming. And thanks to the generous financial support of the NRC and of Harman International, we've done hundreds of them. But apparently nobody else that publishes results has done them. That's the interesting part. It takes time, it costs money. You have to have a sponsor with deep pockets to do this, because it takes human labor as well as material labor. But as we'll see, the expense has been worthwhile because as a result of doing that meticulously careful, monotonous, routine kind of testing, opinions really have become subjective measurements. And the problem that we started with is simplified a bit now, because now we have a way to get opinions from listeners that statistically resemble facts. They can be counted on to be pretty consistent over the long haul. And this is the key to identifying technical measurements and how to interpret them. And it was done by eliminating variables. We eliminated that by making it constant. We eliminated that by making it constant. And we eliminated that by making them blind. And so we were listening, and we ended up just listening to the loudspeakers. And so it's the one we judge. But we need measurements now. This is the final link. Where I started, this is what I hoped would happen, and I didn't find it way back in 1965. And it pertains to the linear performance of devices, amplitude and phase, not nonlinear distortions. That's a whole separate issue. In general, competently designed electronic components of all kinds meet that criterion, and tube power amplifiers mostly don't, because they have high output impedances and they change the sound of the loudspeaker to correspond to the shape of the impedance curve of the loudspeaker, which is ridiculous, but that's what happens. And the LPs are just LPs, they're mechanical devices. Let's start with the microphone, the first transducer in the record reproduction chain. When Sean and I were getting serious about, Sean Olive and I were getting serious about these listening tests, we heard characteristics in the recordings that were, we thought, as bad or worse than some of the characteristics in the loudspeakers we were testing. And so we made it our business to collect a bunch of microphones. Back then, I don't know what the situation is now, but back then, microphone manufacturers didn't reveal a huge amount of information about their product. And certainly not in the same database, same format, so that you could compare one to the other. So we had all this set up for doing 360-degree measurements on loudspeakers, and we did 360-degree measurements on microphones. I'm not showing them to you here. They're in the paper that we did in 1989 it was. There are huge variations in the bass here, for example, and those of you who are familiar with the equal loudness contours know that the equal loudness contours elevate rapidly at low frequencies, meaning we're less sensitive to them, but they also crowd together, which means that a change of 3 or 4 dB at low frequencies matters more perceptually than the same change at middle and high frequencies. At middle and high frequencies, it takes 10 dB to make double loudness. At 40 or 50 hertz, it's probably 4 or 5 dB. So a small change in bass makes a huge difference to our overall impression of spectral balance. And these little problems at high frequencies are quite separate. These had to be, those are colorations. Those are worse than cheap tweeters, in fact. So the microphones picking up the signals are worse than the cheap tweeters on the loudspeakers. So recording engineers confronted with this coming out of their studios or concert hall, wherever they're capturing the sound, need to trust what they hear in the control room. Otherwise, but how can they know what they're hearing? They form opinions, of course. We don't trust measurements, do we? This provoked my first circle of confusion back in 1988. And it says, loudspeakers are evaluated by listening to recordings made with microphones that are evaluated by listening to loudspeakers that are evaluated by listening to recordings made with microphones that are evaluated by listening to, and it goes on and on and on. And the only way out of that circle of confusion is to introduce measurements that you have to trust. And the only way you're going to get to trust them is if we do the proper psychoacoustic measurements, or tests. And that was the hope back in 1988. So what should we measure in a loudspeaker? You stick a microphone in front of it in an anechoic environment. That would be wonderful. That'll give you the on-axis response, and that's a start. But loudspeakers radiate sound in all directions, differently at different frequencies. And we listen in reflective rooms, so these sounds eventually reach our ears, but all sounds are not equally important. In 1983, I got tired of the Brüel & Kjær analog gear that we were using. It was accurate, but terribly cumbersome because you ended up, the only data you ended up with was a pen and ink curve on a piece of paper. You can't do any post-processing with that. So I created a hybrid system. I had a PDP 1103 and some digitally controlled analog gear. And I made a measuring system that would store the data and could perform post-processing on the data. And the first thing I did with it, first thing I did was calibrate the anechoic chamber. So put a loudspeaker 30 feet up in the air, or 10 meters, 30 feet up in the air, and measure it, measure a reference curve, take it into the chamber, measure it in the chamber, and then go to the computer and make it correct for it. So we could we could get correct the anechoic chamber useful down to 20 to 30 hertz. So that was the first thing I did. Then I decided I would try to use the data and the data processing that I could do to predict from the anechoic information sounds that arrive at the listener's ears. That's what we hear. Because what I was reading was about loudspeaker measurements was you measure the loudspeaker, you have to do directivity, polar plots and all this stuff. And I said, we don't hear polar plots. We don't hear sounds at all of these angles, equally certainly not. In a room, you're going to get the direct sound and early reflected sounds and then later reflected sounds. And two ears in the brain operate on these sounds differently from an omnidirectional microphone. So let's see how far we can take this. And that was the inspiration for Spinorama, which is simply to look at measuring the loudspeaker from the listener's perspective. What sounds from the loudspeakers arrive at the listener's ears in a typical room? The first one is the direct sound. That determines image localization, always. It triggers the precedence effect, the Haas effect, some people call it, which determines that even in a reflected environment, you're going to still lock onto the first sound arrival, the direction of the first sound arrival. And it is the spectral reference against which all later sounds that arrive at your ears will be judged. So it has special importance. The second importance goes to the early reflections off the floor, the ceiling, and the side, and the walls of the room. And rooms that we live in have horizontal floors and ceilings, not always, but mostly. And walls tend to be vertical. And so we can simplify the measurements mainly, just certainly at the beginning stage, just by working on the horizontal and vertical planes. Which is what I did. This is the first loudspeaker I really took a serious run at understanding. It was the KEF 105-2. And Laurie Fincham and his gang had exercised the direct sound to be as nearly perfect as they could get it. And they did a very good job, certainly for the time. It was excellent. And they had made the phase linear, which they thought might be important. But in doing so, they kind of ignored the off-axis response. And so the off-axis behavior was not particularly impressive. Why does that matter? Well, because it turns out that it's just the off-axis response that determines most of what we hear in the room. Because here is the direct sound, that black sound, that black curve, that's the direct sound, that's the on-axis response. The dotted curve here is the early reflected sound. Only the first four, just the floor bounce, the ceiling bounce, and the two sidewall bounces. There are others that I should have put in there, but I didn't. And then this is the sound power, the total energy radiated by the loudspeaker. And you add those three together, you'll get that curve. I've just shifted it upwards by 10 decibels to make it clearer. That's the predicted room curve if these measurements were done with any reasonable accuracy. Take the loudspeaker into a room and you measure it in a listening area at 2 or 3 different positions, 3 positions in this case. The bass changes because you're coupling with the room modes in different way, but then above 400 or 500 hertz, it settles down. And the predicted room curve is the big, thick curve. It fits perfectly well. So, wow, I was impressed. Because here, from anechoic data, I had actually predicted a room curve. Not that the room curve tells you what you're hearing, because 2 ears in the brain operate on a sound field in a room very differently from a microphone. But it's interesting that we actually have captured the sounds that do arrive at the listening position, from different directions even. We can separate the direct sound from the early reflected sounds from the reverberant sounds. So at the low frequencies, it's the sound power that dominates what we're hearing. In the middle frequencies, it's direct and early reflected sounds. And at the high frequencies, it's the direct sound only. It's the tweeter just talking to the ears. Those are the measurements that I was making at the 60 to 75 degree off-axis curve here. Those are the measurements. And look how well just that set of measurements fits. Below 7 kilohertz, it nails the prediction curve. It nails the real room curve. So what you're measuring when you measure a room curve with this omnidirectional microphone, you're measuring the off-axis, the far off-axis performance of the loudspeaker. When I see measurements on a loudspeaker that go 0, 15, 30, 45, and they stop, hey, it's beyond that where things get interesting. This is all just a listening window. That's where the audience is. Here's nothing. I don't care about that, but I care about what happens out here because that's the wall bounce, the ceiling bounce, the floor bounce, and that sidewall bounce. And those are the second loudest sounds that arrive at your ears. Second observation. I mean, this is 86, I'm sorry, almost 39 years ago. You'd never guess it, right? If you look at that room curve, if you've measured it or predicted it, doesn't matter. If you look at that room curve and you say, well, that's not very good. I can make that better. Give me an equalizer. I'll just add a few parametric filters and I'll fix that. But as soon as you change that room curve, you've changed the on-axis response, which is the only good thing that loudspeaker had. You've ruined a good loudspeaker. Well, it wasn't a perfect loudspeaker, but it was better than it would be after you've tried to fix the room curve. So equalization cannot change loudspeaker directivity, and directivity determines the room curve. And the solution is a better loudspeaker. You can't fix that. Room curves are results, not targets. Remember that. And I'm saying this knowing that there's a business out there that is telling the whole world that you buy any loudspeaker and push this magic button and it'll make some funny sounds and make an equalization change, and we're going to make that loudspeaker perfect. And if they want to really instill belief in your minds, they'll say, we're going to match the Harman curve. I created the Harman curve. And the Harman curve is the steady state room curve of highly rated forward-firing cone and dome loudspeakers, and that's all. If you take a brand X loudspeaker with unknown characteristics and stick a microphone in a room and match the Harman curve, is it going to sound like that loudspeaker that I described? Not a chance. But it's a business, and so now, what happens then is they say, well, if you didn't like that, here, try this other room curve. And if you didn't like those room curves that we give you as options in our little algorithm, we'll allow you to draw your own room curve. How many of you have ever seen that? Anybody here ever done a room curve? Yeah. You draw your own room curve, play your own favorite music, and if you like your music, that's your room curve. Well, rubbish. I mean, that's a fixed tone control, and recordings are not consistent. Anyway, considering the many timbral and spatial effects of direct and reflected sounds, what we measure with these simple systems is not what we hear. Here, let's just look at that same database, that for the 1986 database of mine, or set of data, and consider listening distance. We're going to that set was calculated on the basis of listening at 12 feet in my prototype IEC room. But let's just move the loudspeakers forward to a midfield position or near field position. And as you do so, the direct sound goes up. And as you do, here's the direct sound at the midfield 6 foot range. Here's a 4 foot range. As you get closer to the loudspeaker, of course, the direct sound becomes more prominent. And eventually, the room will be less prominent. The off-axis performance of the loudspeaker will be less prominent. It's going to be, what you hear is determined by the on-axis performance of the loudspeaker. You have only one thing to design for. And if you can't get that right, you're totally incompetent. But the other way of approaching it is to actually absorb the sounds, the reflected sounds in the room. And there are two international organizations, ITU and EBU, that have well-used standards that say, well, you've got to get the reverberation time down to about 0.2 seconds. That's really quite low. And you've got to reduce all early reflections. Read the fine print. It's all early reflections by 10 dB. That's floor bounce, ceiling bounce, sidewall bounces. And this is crude. This is a really very, very crude illustration. It's not technically correct, but it'll give you the principle of it. If you're going to do that, if you're going to attenuate, put absorbing material on all the surfaces of the room and capture those first reflections, you drop it by 10 dB. You probably ought to do it above the transition frequency, because down here the room resonance the rules change. You're into the room resonant mode. Here it's specular reflections, and if there's some legitimacy to doing it over this particular frequency range, because resistive absorbers only work at middle and high frequencies anyway. But what you've done is you've created a disparity. I mean, you've destroyed the spectral balance. You've got to fix that somehow. If you follow the ITU and EBU recommendations, they say do it only above 1 kilohertz. Now, why on earth would they choose 1 kilohertz? It's right smack in the middle of the spectrum. You're going to put a step in the spectrum. I mean, it would never happen as a step. It would be a gradual transition. But why would you do it at that frequency? But they did, in their wisdom. There are other problems with that. Okay, if you do a mix and you're in a dominant direct sound field, whether you are in the near field or you are in a reflection-free room, it doesn't really matter, so long as you're in a dominant direct sound field. One pro is that the loudspeaker resonances are less audible because you're not hearing any room reflections. The con is that the timbral features, the resonances in the recording are less audible. So you're probably going to add a little reverb to the mix to sweeten it. So that you can do, which is good, but what you're hearing is not what your customers are going to be hearing, because your customers are going to be listening in a room. Loudspeaker directivity variations are less of an issue, because the room, you're listening so close to the loudspeaker that the room is almost not a factor. And the room is less of a factor, that's the other thing. And loudspeakers with flat and smooth on-axis performance are becoming very common and quite inexpensive, as I'll show you if I have time. I'll show you some examples. But the soundstage and imaging that you're hearing in this near-field situation are different from the total than the consumer hi-fi playback, or most people in their domestic listening situations where you're not hearing what your customers are hearing. And something that a few people know about, not everybody, but the phantom center image has if you're sitting in the stereo sweet spot and the direct sound arriving from the loudspeakers is subject to interaural crosstalk, that the sound from the left speaker arrives first at your right ear and later at your left ear, and vice versa here and here. So you have comb filtering occurring at the ears. And for the center image, that comb filtering will be most dramatic, and it results in about a 1 octave wide, 10 dB deep hole in the frequency response for the center image featured artist in the recording. And you can play pink noise, monophonic pink noise, and lean a little bit left and a little bit right, and you can hear it when you're in the sweet spot. It's dull. You hear the null, you hear the dip, and you move a little bit left, it gets brighter. You move back to the dip, brighter, dull, brighter, dull, brighter. So when it's dull, you're in the sweet spot. And you can't fix that with equalization because it exists only for the person in the sweet spot. If you fix it with equalization, everybody else in the room will hear a spectral bump. Everybody with headphones will hear a spectral bump. So you can't equalize that flaw. It is a fundamental flaw of stereo that we are burdened with so long as we listen to stereo. And you're 4 feet from any hard panned images or voices. Is that a good idea? Well, anyway, you may like what you hear, but what you're hearing is not what your customers will hear. So by all means, feel free to use it for mixing, but before you're through, listen to it in a situation where the room is involved, because that's what your customers are going to be hearing. All those who are not listening in headphones. But we listen in small rooms. Now, how's my time going? We were going to make a break at some point.
Break when you're ready.
Okay, well, in about maybe 5 or 10 minutes. Okay, we listen in small rooms that have low frequency resonance within the musical frequency range. And when you think about that, and just think of yourself, you sit down in your listening room or in your control room, doesn't matter, small rooms, they're all small rooms. You can't ignore the resonances in the room. I go to live concerts, and one of the pleasures of going to a live concert in a big space is there are no room resonances that are audible. And the bass is just, every note is there. They're all at the right level. Nothing is missing. The kick drums and the toms are all punchy and impact. Nothing it gets in the way. Go home and I listen to a recording of the performance and I hear a small room. Sorry. And I fix room resonances, and you can fix them up to a point, but you can't eliminate the total illusion that you're sitting in a small room. And as long as you realize the brain knows you're sitting in a small room, creating the illusion of being in a concert hall is an uphill battle. Let's just say that at the very least. Reality versus prediction. Here's taking the loudspeaker into a room and measuring it, moving it 18 inches, that far, measuring it again, moving 18 inches. That's all. Speakers are all within a 3-foot circle. And those were real measured bass differences. And that's the prediction that I calculated. So what we have really is a region where the room is in control of what we're hearing timbrally, and a region where the loudspeaker is responsible for delivering the sound to our ears. And we can, from that data, calculate a steady state room curve, but the steady state room curve is not a reliable indicator of what we perceive, because 2 ears and the brain are different. Now, Dr. Arthur Bernade, I don't know whether any of you know of this man, but he was a physicist and a musician and a very insightful person. And he gave me, before he died, he gave me a bunch of his writings. And among them was this lovely little cartoon that I said, well, that sums it up. And he said, but basically this is a central paradox, he called it. And it was, you go to a concert, the musical sources are obviously well defined, the voices and the musical instruments. And what you hear sitting back in the audience is very well defined, the voices and the musical instruments, but what happens in between is chaos. And if you measure the high resolution transfer function from from the stage to any position in the room between you and the listener, you're going to get different curves, very complicated curves. It's going to be a horrendous looking mess. Yet 2 ears in the brain make sense of it. And that's fascinating because it suggests that if it's possible to acoustically define the source, describe technically the source, we should be in a good position to predict what we would perceive. And then if that's correct, then it'll apply to the reproduced sounds as well. If we can describe the loudspeakers sufficiently, we should be able to predict what we hear. Except at low frequencies, because at low frequencies, woofers and subwoofers radiate sound omnidirectionally, and there's no directivity factor. And the wavelengths are long compared to the room dimensions, and so there's no discernible direct sound. So below the transition frequency, steady state room curves are in fact useful. They're definitive information. But I'll point out again that room curves are not targets, and the widely circulated Harman curve are results for highly rated forward-firing Conan dome speakers. And equalizing a flawed loudspeaker to have the same room curve does not ensure anything. They are not targets. And I think I told you this earlier. I got ahead of myself, but basically, they're tone control adjustments, and we should use neutral loudspeakers and tone controls, and use the tone controls to compensate for variations in program. I listened to some recordings a few weeks ago, just out of curiosity, and went on Tidal and played some music from different origins, different periods, and I found the level of bass. I could adjust I had a bass contour tone control, and I had a subwoofer level about below 80 hertz I could turn up and down. And I was turning the bass level up and down over a range of about 10-15 dB. Some recordings had no bass. You had to really push it hard to hear any bass at all, particularly old rock and roll records. But then modern records, some of them had horrendously overblown bass. They just lift you out of the chair. So they had to be turned down. You need a bass control. You need tone controls. If you're fussy about spectral balance these days, you certainly need tone controls. But start with a neutral speaker, because then you always have default go back to neutral and you hear what was on the recording. In 1986, these double-blind listening tests provided the clue that of what people were really hearing when they complained. Because if you look at the highly rated ones, 7.5, 7.9, they're pretty smooth on axis. Half a point less, getting a little less smooth. Further point down, pretty not very smooth at all. On and off axis, getting smooth, less smooth, less smooth as you go down in the score. Look at phase responses. They're smooth, and less smooth as you go down. And what we're seeing here are clues to resonances. Every little hiccup in that phase response curve is caused by a resonance, a mechanical resonance in the transducers. And the best loudspeakers didn't have any audible resonances. You don't see repeated bumps in the curves here. They're undulating, but not bumpy. And you don't see any hiccups. We had a little hiccup there maybe. But in general, clearly, resonance is what people were detecting, and this is 1986. So people hear and do not like resonances, so we have to detect and measure resonances. A useful technical fact is that loudspeaker transducers and prominent room resonances are minimum phase systems, or behave like minimum phase systems. And what happens is that if you have a parametric equalizer and you dial it into the right frequency and the right Q, and dial down the bump in the frequency response curve, you correct not only the frequency response curve, but you correct the time response. So powered loudspeakers and equalizers with equalization certainly have advantages, and you'll see most professional recording monitors now are active powered loudspeakers for that reason. They're very good. They can be superb. In 1988, Sean and I examined the just audible thresholds for resonances. And it clearly depended on what we were listening to. Pink noise was the most revealing of all. Rock and roll, the least revealing. So you can be good enough for rock and roll. It's not a joke. Symphony orchestra was nicely in the upper middle category of what we can detect. And these were thresholds determined in an anechoic chamber. And just think about it, some of them are pretty low. That is about a decibel for a low Q. And when listening in a reflective environment, these thresholds are even lower. So we are able to hear a small fraction of a dB change in level in a low Q, relatively broadband spectral event. And tone controls tone controls and wide broadband EQ and tilts and so on fall into that category. You can hear a tilt of 1 dB from 20 to 20 kilohertz. That's roughly the detection threshold. So these are the audible thresholds. These are resonances at audible threshold with listening to the most technically revealing signal, which is pink noise. Q of 50, Q of 10, Q of 1. Obviously, high Q, lots of ringing. Medium Q, some ringing. Low Q, almost no ringing. Hit it with an impulse, lots of ringing. Little ringing, almost no ringing. And the interesting thing about it is that those are all equally audible. Those are threshold of detection. Lower amplitude, you don't notice it. And with rock and roll, that Q of 50 can be 10 dB high. You'd look at that and be very, very alarmed, but you play your favorite rock record and you may not hear it. In 1991, my phone rang. It was a headhunter, and one thing led to another, and in 1991, I became corporate vice president of engineering or acoustical engineering for Harman International in California. I set up a research group, hired Sean Olive. Later on, I hired more people, and we carried on doing the research. And this is a good point to break. Thank you.
Fantastic. Thank you very much. And the Blue Jays game, I think, is starting. So, if my wife said nobody's going to show up, it's a Blue Jays game, and I'm like, you don't know my people. So thank you all for being here. We'll take a 12.5-minute break. So 13 minutes in, we'll start this back up again. Thank you.
The bathrooms are just by the elevators, so this way, to the east, across the atrium, and then to the left. So if you see the elevators, the washrooms are just behind the elevators.
Well done, Finley. Look at this. You never get old. Hey, folks, we'll get going in 1 minute. 1 minute. All right, everyone, if you could take your seats, that would be appreciated. I'm talking to you, Frank, down in front.
Okay, we're back. Everybody ready to go? Well, when I got to Harmon, it wasn't very long before I had to convince people that they needed to do double-blind listening tests, and nobody had Harmon that could remember ever doing it before. So there was there was some difficulty getting people to agree to do it. And there's a paper about Sean and I had to do a double-blind versus sighted test with our engineers to convince them that people could be biased by what they see, and they were eminently biased by what they saw. And I was talking to somebody in the hallway earlier about this and saying, and really what we concluded was that in a sighted test, one hears less than in a blind test. Because in a sighted test, you are predisposed to believe certain things because you see them or you know them. For example, you could do the same test with a loudspeaker in different positions in a room, and in a blind comparison, you'd hear the differences because obviously it couples to the room in different ways and it makes a difference. It's not subtle. In a sighted test, the differences disappeared. People would say, well, it's the same loudspeaker. So they give it the same score. Same thing with program material. Speakers are in the same locations now, but we're changing the records. And different recordings give slightly different scores because of different spectra and so on. Recording are not all neutral. And that's normal. And as soon as you let them see the loudspeakers, those differences went away. I know that's the same loudspeaker, so why should I give it a different score? On and on it goes. Anyway, so we had to set up a little group to administer blind listening tests, and some of the engineers really grappled onto it and went running with it, but others dragged their feet. What was amazing about getting this approval to do it was Harmon probably spent $1 million or $1.5 million almost immediately just to get the facilities of the engineering group set up and our group set up. And then we hired people that were continuing costs. But most amazing, they allowed us to publish the results. It was not kept as company secrets. Because there are companies in this world now, you know, that won't allow that at all. No publications are permitted. It's all corporate secrets. Well, Harman allowed us to educate our competitions. And interestingly enough, later on, it was our competition who set up the ANSI-CTA standard. Anyway, an interesting story. So I hired Sean Olive, who was then retiring from Harman, from NRC, and we just carried on. I hired more people. So the new anechoic chambers allowed us to, which we built, allowed us to do really very accurate spinoramas, much more detailed and faster, at 4-foot wedges and so on. And we, you know, because I'd done the room curve predictions, we knew we had to measure the direct sound and the reflected sound separately because we hear them separately. And the raw anechoic data was 70 measurements, so this is the basic, the basic frequency response measurement on any loudspeaker, which would be 70 curves measured at 10-degree increments and on 2 orbits at 2 meters, which is near enough far field for most consumer loudspeakers and professional monitors. We did them at 1/20th octave resolution so we could see even high Q resonances. Alan Demontier did a survey of typical domestic listening rooms from which we determined which off-axis angles mattered most for various things. This would be this angle range for the sidewall reflections, left and right, and ceiling reflections, floor reflections, the listening window, and then the on-axis, of course. The on-axis curve was the first curve in the spinorama, and that's the direct sound. The listening window is plus or minus 30 degrees horizontally, plus or minus 10 degrees vertically, so it's a spatial average of 9 measurements, which gives us 2 things. It gives us a spatial average, which allows us to separate, to begin to separate acoustical interference irregularities in a curve from resonance, from irregularities that are attributable to resonances, because resonances we hear very easily, acoustical interference we may or may not even be aware of. Early reflections, you know about those. Sound power, the total energy radiated in all directions, which will eventually reach our ears after multiple reflections and great attenuation. There really is no reverberant sound field in a small domestic or a small-sized room. There's not. You hear a decay of early reflections, and that's about it. And from the sound power and the early reflections curve, we can calculate the classic directivity index, which is the difference between the sound power curve and the original one was with the on-axis curve. But the on-axis curve often shows interference effects, which you don't really care about. So we use the listening window as the reference. So it's the difference between the listening window curve and the sound power curve that gives you the DI sound power. And we do a difference between the early reflections curve and the listening window curve to give us the DI for the early reflections. So from a listener's perspective, this is more relevant than the sound power curve, even though the sound power curve is the one you'd find in the dictionary definitions. And this loudspeaker that I'm showing you received very high sound quality ratings in many double-blind tests. In fact, it never lost a double-blind test. It statistically tied with other equally good or comparably good loudspeakers, but it never lost. And as shown in 1986, above the transition frequency, the room curves are dominated by early reflections, but again, remember they are results, not targets. And in this case, because we did a much more elaborate calculation of the early reflections curve, it matches the room curve to a higher frequency. You now get above 10K before it starts to depart, and because we didn't include any direct sound in we didn't add any direct sound in. Doesn't matter actually. So here's an instructive experiment using a flawed loudspeaker. This is the original loudspeaker. It has a medium Q resonance, medium Q, a low Q resonance, and a medium Q. Now the low Q resonance is the big problem, because you remember that low Q resonances we can detect at a fraction of a dB amplitude. And this is a biggie, so it really howls. Although when you look at a curve, your eyes are more attracted to those than that. And this is the room curve, the steady state room curve that resulted from that particular spinorama. So how are we going to fix that curve, that loudspeaker? Well, we can EQ the room curve, which we did. We hooked up an automatic EQ system. Now the automatic EQ system has no human intervention. It is just a dumb device that's going to smooth the curve, whether it's a peak or a dip, whether it's a resonance or an acoustical interference. Now we had an acoustical interference in the crossover region. That should not be equalized because it's a non-minimum phase. It's a non-minimum phase property. It has a time delay associated with it. So that should just be left alone, but in fact it fixed it. Anyway, it smoothed the room curve very nicely. We take the loudspeaker back into the chamber and see what happened. Well, it found the low Q resonance and fixed that, got rid of the low Q resonance, which was the most audible problem, but it didn't find and fix these medium Q resonances. If we take the loudspeaker back into the chamber and flatten it on axis, make the on axis curve flat, then the room curve is not as pretty, but the listeners preferred this. So this is the loudspeaker which has the fewest audible resonances, because the measurement system in the anechoic chamber could find them and fix them. So anechoic chambers matter, anechoic measurements matter, and they matter most if we can really prove how important they are. And we found the excuse to do so. One day I was called to the CEO's office, and he said, "Look, Toole, we pay you a lot of money to make sure our products are good. Could you explain to me why some Harman products did not do well in this Consumer Reports rating of hi-fi loudspeakers?" I said, "Oh God, it's their rating methods that are wrong, and it's been known for decades. In fact, I did a test back in when I was at NRC, and I showed it to them. There were two engineers who came to NRC, and I showed them their results, my results versus their results, and there was a minus 0.7 correlation coefficient between the loudspeakers that I was showing them, which meant that from their product reviews, you turn the page upside down, you get a better idea of what's good. And they went away and they said, no, we're making money. So they didn't say it in those terms. That's obviously the message. Don't rock the boat. Anyway, I said, if he challenged, he says, well, could we prove they are wrong and just get rid of them somehow? And I said, yeah, probably, but it's going to cost money. Take time and cost money. And amazingly, they agreed. And so Sean Olive and I sat down and thought about what we knew about interpreting graphs. What in the graphs would our eyes see that would lead us to believe that there was an audible problem? And from that collection of subjective/objective data, we worked out a possible program of by which he might be able to apply a multiple regression model that would predict loudspeaker preferences in normal rooms using anechoic spinoramas. And so here's part one of the test, which was something we've been doing at Harman for years. Actually, we routinely tested our own products double blind and measured them. We routinely tested our competitors' products and listened to them double blind. So we had a fairly large database, 70 loudspeakers at that particular time, where we felt we had data that we could confidently use. So there were subjective ratings on a scale of 10 where people were listening in a normal room compared to calculated preference ratings based on spinoramas measured in an anechoic chamber, and the correlation coefficient was 0.86. One would be perfect. This is not shabby. We were very satisfied that from the anechoic data we could come close to a prediction of what was happening in a room. But the 70 loudspeakers that we used in this original test included loudspeakers of all prices and sizes, and which included bass extension. A big floor stander at $20,000 a pair is going to have way more bass than a little $200 bookshelf you can carry under your arm. So that people would give a higher score to something with more bass is totally understandable. It's also understandable then that when Sean's analysis revealed that about 30% of the factor weighting in these sound quality ratings had to do with low frequency performance, low frequency extension, and low frequency smoothness. So we did a separate experiment which involved 30 small bookshelf loudspeakers. These were the loudspeakers that had similar bass performance. And we got a correlation coefficient of 0.995. That's 1. There were no errors in the ranking of the subjective ratings versus the calculated ratings of those small bookshelf loudspeakers that had similar bass extension. So do we know what we're doing? Just maybe. Now these were the loudspeakers that had been evaluated and rated by Consumers Union, the one that called me to the director's office. And when we compared our ratings to their ratings, the correlation was small and slightly negative. So it was minus 0.22, meaning that their ratings were essentially random. It wasn't negative. You didn't turn the page upside down. You just ignored it because you could throw a dart at the page and you'd probably pick it just as well. So we sent them the results of the tests, knowing that they'd be interested. And they came back. And we had a little discussion, and they, being who they were, they could not adopt a manufacturer's method of measuring. It would show bias. So rather than show bias, they stopped testing hi-fi loudspeakers, to the great relief of manufacturers and to the great benefit of consumers. Science works. But that's Harman. I mean, it's a profit-oriented company, but by golly, they spent a lot of money doing good things. I have very kind feelings about them. Here are some visual correlations that are pretty impressive. That's a low-scoring loudspeaker. Looks pretty bad. A higher-scoring loudspeaker, not perfect, but not terrible. A higher-scoring loudspeaker and another higher-scoring loudspeaker. These are, in fact, are in a statistical tie. All of those loudspeakers have been reviewed by the audiophile magazines, and all of them received rave reviews, leading the readers to buy any of them and thinking they'd take the state-of-the-art loudspeaker back to their home. These weren't inexpensive loudspeakers at the time. This is where, price was not a criterion of quality at all. If I showed you that, would that make a difference? And yet that's what consumers are going to see. And if you're a fashion, if you're an aficionado of electrostatics, you'd probably be attracted towards that. If you think B&W have a secret with their top-mounted tweeter, you'd probably believe that. That's an Infinity, that's a Revel. But in fact, none of that matters. How it looks does not matter. The transducer technology, whether it's electrostatic or cone and dome or cone and horn, none of that matters. Marketing claims don't matter. These are all not reliable indicators of sound quality. There are good electrostatics and bad electrostatics. There are good cone and dome and bad cone and domes. How it measured and how it sounds are the only things that matter. And measurements are more trustworthy than casual opinions and subjective reviews. So we've got to be able to trust our measurements. And this is another bit of evidence that measurements put us on the right track. Here's Sean did a test using 268 listeners. That's a lot of listeners. And he did 4 at a time, and he did 3 at a time. You can see that the winners are still winners, and the losers are the losers in all of them. And the winners are the ones that have smooth and flat curves. That's That was P. There's I, it's a little bit lumpy, has a little bit too much bass. B is off, not flat on axis, terrible off axis. That's down there in the middle ground, and that's the electrostatic. It has terrible resonances. And so, measurements do indicate what's likely to sound good. Whose opinion do you trust? Do you trust our trained and selected listeners? These are the ones that have good hearing and are trained to hear resonances. They give us really good answers. Now, these bars here are listener performance based on a statistic called the FL statistic. It's a measure of the consistency of repeated judgments and of the strength of the rating differentiation. So good listeners give you consistent answers with very little variations, and they will give you larger differentiations in score between that speaker and the speakers that are less good. People who aren't sure of themselves don't give very much variation in their scores, and they give you a lot of variation in their ratings. And a lot of variations in their scores. Retail salespeople did very well because they spent a lot of time listening to loudspeakers in the stores. Audio reviewers, the brave ones who came, did reasonably well. They're just average. Our own brand sales and marketing people were dreadful. So these are the people who are out in the field representing our brands. God bless us. And students who have no experience, well, they just need to have experience and learn. But the beauty of it all is that even though these had different FL statistics, they varied in their consistency and the strength with which they differentiated the ratings. They all agreed on what was good and bad. The ratings are always the same. It's interesting. So unless you have defective hearing, you're probably going to do well. And this is where the ANSI standard came out, CTA standard. And it was initiated by our competitors who saw value in what we were doing. And we helped out when they asked us for specific information, and a couple of my drawings are in the standard, actually. So historically, useful measurements have been missing, and this has changed. Historically, you didn't know what a loudspeaker measured like because nobody published it and nobody measured it in the real world. Very few, at least. But now we know what needs to be measured. And we have anechoic data generated by these Klippel near-field scanners that are semi-miraculous. Measure anechoic data in ordinary reflective spaces, and they are increasingly available. And some private owners have them, and they publish spinoramas on the internet. And a few conscientious and courageous manufacturers publish their spinoramas on their data. You go on their internet surface, you find spinoramas on all their measurements, all their products, or at least anechoic data on all their products. And that's good. Because now that this data is becoming increasingly available, there is no place for mediocre products to hide, and for manufacturers of those mediocre products to hide. Marketing is not going to compensate for the fact that we know how this thing is going to sound. Good products are recognized, which is wonderful. Parametric EQ based on spinorama data, not room curves, can improve many loudspeakers. So if you see spinorama on a loudspeaker and you say, well, it's almost good, it's got this and that little wobble to it, but you have an equalizer and you have that data, you can fill in the wobbles, and you've turned a good speaker into an excellent speaker. And so anechoic data is powerful stuff. And it means that there are going to be many, many, many more good-sounding loudspeakers in the world, and there are. And the loudspeaker world really has changed for the better. But we're not done yet because we have the damn small room to deal with. And here's the same loudspeaker measured in 6 rooms. I did this in 1984. And I listened to the loudspeakers in those rooms, and there were boomy notes and there were missing notes. And no amount of tone-controlled twiddling could even come close to compensating for it. So I just said, well, here's a problem we got to solve, because no matter how good the loudspeaker is, these room resonances are going to screw it up. And Sean showed that 30% of our preference ratings are related to bass. Bass extension is the loudspeaker. Lack of smoothness is room resonances. And the greater the low bass extension from the loudspeaker, the more room resonances are energized, and all rooms are different. So we're going to have to deal with this in the room. We can't deal with this at the factory. This is something you're going to have to do after the system is set up. You know about these classes of standing waves, the axial modes that go rectangularly between parallel surfaces, the strongest modes because they have only two reflections on each cycle. And then the tangential modes have more reflecting surfaces, so they are slightly less energetic. The oblique modes are rarely a factor. We hear those dominantly. Occasionally we hear tangential modes, but rarely do we hear oblique modes. And this is a lovely little GIF of a standing wave, third order standing wave. So they're third order because there are three nulls. And on opposite sides of the null, as the sound is increasing, it's decreasing. There's a little seesaw around each null. And it's important to know that, because we're going to use that to our advantages. Here's how we normally describe these standing waves. I mean, we have a first order with a null in the middle of the room. We have a second order with two nulls. And we have a third order, this one, with three nulls. And on each side of the null, as you cross a null, the polarity changes from plus to minus, minus to plus, and so on. Now, how are we going to deal with these things? Well, bass traps work. They absorb energy by allowing the sound to move them, and they dissipate heat. They're large, they're unattractive, and they can be expensive, but they do attenuate room resonances. But they also reduce system efficiency by absorbing energy, obviously, because you're turning bass energy into heat. You pump up the room with bass energy, and you absorb it and turn it into heat. In 1988, I built a custom house in Manotick outside of Ottawa, and I had a terrible bass boom in my it wasn't fancy, my new home theater. And it was very minimal, actually. In 1988, that would be the beginning of home theater. Bass traps were simply not an acceptable solution, so I applied physics. And knowing what I just described to you about the polarity changes, in the original, I had a woofer in the corner. The television was in the corner, of course, and we sat around looking at the television, listening to sound. And that subwoofer generated horrendous bass boom, and this is the dotted curve that it generated as, missing bass and Johnny one-note bass right there, 52 hertz or thereabouts, just howling. So I said, no, what happens if we use two subwoofers, one there and one there, because this has opposite polarity lobes, so that woofer and that woofer are in phase, driving an out-of-phase standing wave, so it destructively drives it. So that standing wave will not be excited. And that one is in this lobe, this one is in this lobe, opposite polarity again, so that standing wave will be cancelled. So in theory, seems to me, if we have these two subwoofers here, nothing there, and they're in phase, identical subs, it's going to cancel that standing wave, and it's going to cancel that standing wave. And lo and behold, it does. And the solid curve is what I measured. And you can see that the peak has been turned into a cancellation null. It's just a sharp null. It was too good. It really did cancel it. And not only that, but once it canceled that, it actually filled in a lot of the other spaces as well. So and in the time domain, you can see the TEF12 measurements of the ringing. Sub 2 rang, sub 3 rang by itself, that rang by itself, that rang by itself. But you put two together and the ringing drops about 12, 15 dB right away, bang. So the time domain has been fixed. That's nice. So now we have a technique to manipulate room modes by positioning in single and multiple loudspeakers or woofers. If we start with a woofer against the wall, it's in the high pressure region of that particular null, high pressure, low pressure, high pressure. And at high pressure, a pressure source at a high pressure region couples dramatically, so that'll produce the highest curve. You move that speaker towards the center of the room, and you're coupling less well, and you generate that curve. And you move it to the center of the room, you're in the null, and you generate that curve. It's not, the pressure source is in a velocity region of the standing wave, and so it couples very little energy to that particular mode. So we have a volume control simply by sliding our subwoofers around for that particular mode. You have two subwoofers. If you have one sub by itself, it generates the maximum energy standing wave. You put two together identically, and the standing wave basically goes away. It's cancelled, turned into a null. You can put a volume control on one of the subwoofers, and you can turn the standing wave up and down. So now we're beginning to get some control over standing waves, not just turn them on and off, but turn them up or down, which means that if we have a target function in mind at the low frequencies, we can, and we know there are certain modes that are involved in generating our bass, we can turn them up and down to get them at the optimum level. Here's what happens when you to multiple. This is the first three standing wave orders. This is the first order is cancelled with two subwoofers. The third order, the odd order one, is cancelled also with two subwoofers, but the second order one is amplified. Well, if you have a choice of energizing three room modes versus energizing only one room mode, you take that alternative because you could then have only one filter to deal with, one filter frequency you designed to cancel that particular room mode. However, if you are able to, and you can, slide the subwoofers to the 25% locations, you're in the nulls for the second order modes, and you're in opposite polarity lobes for the first and third order modes, and you've really attenuated all three modes. And if you look carefully, that's stereo. And stereo signals are often monophonic at low frequencies. And so for as long as we've had stereo, we've been canceling modes, not knowing it. We can sit in the stereo in the center of the room in we would think, well, that's a null. We can't sit in the center of the room. Well, you can because you have two subwoofers and that mode doesn't exist. Interesting, eh? So always do low frequency measurements with all subwoofers operating, all woofers and all subwoofers operating at the same time, because that will determine how the complex room mode structure is energized. I see people setting up one subwoofer, they calibrate that, and they set up another subwoofer and they calibrate that, and then they sit back and listen to it. Well, no, you've done, it doesn't work that way. You have to drive all the subwoofers simultaneously. And this is the kind of thing we're doing. As I said, when you cancel two out of three room modes, you cancel the first and third and left with the second. This is the situation you end up with. Four subs, and you cancel that. You're only left with the second order axial and tangential mode, but it leaves you 6 by 6 foot area in this particular room, and other areas off to the side where you can sit and hear good bass. You just avoid the nulls. You can have put woofers in the corners, which is a much more efficient system because you get the corner gain. And when Todd Welty went through the exercise of, I hired Todd because he had his considerable MATLAB skills, which I lacked. And he went off and optimized it for generic rectangular rooms. And the book and the website contain enormous detail on all of this. This is just very simplified. But you end up with a bunch of recommended subwoofer setups that vary in efficiency, and they vary in the extent to which they reduce the seat-to-seat variability. And this is about as good as it gets. This is an optimized system. Interestingly enough, you can put a subwoofer at each of these locations in the middle of the room, And that also works. In my present room, I have one here and one here, and I sit right there. Excuse me, I'm sorry, coughing. My voice gets a little raspy. If you're going to equalize a room mode, you use a parametric equalizer. You have to measure with high enough resolution to be able to identify the center frequency and the Q, and if you hit the center frequency right, and you match the Q correctly, you do attenuate the resonance. The ringing basically goes away. If you don't match the Q, then you simply attenuate the resonance, and the ringing stays. So you've got to, if you're going to equalize, you've got to measure with high resolution and equalize with precision, and then you get the optimum result. Otherwise, you just get a better result, but it's not optimized. So sound field management was the next development, because when I got to my new home in California, I didn't have a rectangular room. And so I called Todd into my office and I said, I need another solution, Todd. And it's for me and anybody else in the world who doesn't have a rectangular room. And that's a lot of people. I had a section of one wall that was open to the next room. So he developed a digital processing system which allowed adjustment of gain, delay, one parametric filter in the signal feed to every subwoofer. And the parameters for these parametric settings were determined by an optimized algorithm working with measurements that you make from every sublocation to every listener location. So you make complex full transfer function measurements from every sublocation to every listener location. Analyzer will compute the optimum solutions, give you several solutions. You have some flexibility where the subs are located. They don't have to be the same. Unfortunately, SFM by itself is available only in Harman products, but the inspiration that came from that set various intelligent minds alive, and there are other alternatives on the market now and more coming. It's a very good idea. This was my home theater in 2000. It's a multi-purpose whole family room with casual seating. You can see the seat variations were huge. After SFM, seat variations are small. The amount of sound energy being radiated into the room is considerably reduced. This is like 200%. This is 100 plus 6.3 plus 25 plus 6.3. So we're radiating less energy into the room, and yet the average sound level is 10 decibels higher. That's 0 on average. Now we're up to 10 with less variation. So we gain efficiency. Subs. So we have a situation where science is now contributing to art itself. It's our business, and good sound is our product. Conclude, neutral, technically accurate, audibly resonance-free loudspeakers now exist at all price levels for professional users and entertainment users, consumers. They are more reliably identified by interpreting anechoic spinoramas than by forming opinions under the listening circumstances available to most people. I don't care about your opinion until you've done the test in the right way. All loudspeakers are at the mercy of a small room. I'll let you read it. The listening room is the weakest technical link. But the weakest link really is human nature. We want to believe what we hear, even if it's unrealistic to do so. That's it. Now, what I can do, it won't take anything out of my voice. I'll just show you some spinoramas on professional loudspeakers and consumer loudspeakers, and the data speaks for itself. So can the recorded arts be reliably communicated? Absolutely. Is the circle of confusion broken? It can be. It's getting closer as the days pass. Here's what a professional can buy for $350. A powered monitor. Look at that. Doesn't get much better. $350. You want a little more power out of it? $380 will buy you a horn-loaded 5-incher. That's not shabby. You want to spend a lot more money? I have evidence of a lot more of these. $9,000. Look at that. That's Genelec. Ilpo Martikainen, the person who started Genelec, he's dead now, unfortunately. He hooked up with my work right from the very beginning, back in the 80s. And every time I'd meet him at an AES conference, he'd drag me into his showroom and play for me classical music, Mozart and Beethoven, through all of his loudspeakers, from the little ones to the big ones, and he'd sit there with a great smile on his face saying, yes, they sound alike and they sound pretty good, don't they? He said, science works. No, he knew it from the very beginning. Now, this is an interesting one. This is a cardioid loudspeaker from the Netherlands. Martin Mensink is the guy who designed it. And it goes from 20 hertz, legitimately, to 20 kilohertz, legitimately, and a directivity that is really basically flat. Look at the directivity. It's amazing. 12,500, it's not cheap, but you get a full range system out of it. Or you can have this, which will bring blood from your ears if you want to play it loud enough. But otherwise, we've compared that to the very best Conan Dome speakers, and it's a good horse race. So you can, the pros are in good shape. If the professional people care to go find the measurements and buy the products based on the measurements, they can have neutral sound and inexpensive neutral sound. Consumers, look at this for $200, a TV sound bar. Now, it's not surprising that it's good. It actually was designed by Alan Devontier's group at Samsung, my research group for years. And Samsung hired him away. He set up his own lab duplicating the Harman one, a little more modern, actually. But then Samsung bought Harman. So we all ended up in the same happy family. But for $200, give me a break. 5.1 simulated. Here's 3-channel. Look at that. I mean, I've heard this. This is hi-fi, folks. This doesn't play terribly loud, but it's high fidelity. It's a TV sound bar. Here's a little wireless, smart stereo speaker you can talk to, and it'll turn your lights on and off. And sound good at them while doing so. Here's one you can hang on your wall. Buy it from IKEA. It's designed by Sonos. They know what they're doing. They have my book, actually. I knew. Here's a Canadian, the PSB, a little $700 a pair thing. It's just fine. And this is one that came out of the blue. Look at that. That's a passive loudspeaker from Korea. I don't know anybody who ever heard of the company before, but it's just as good as it gets. Another Canadian product that's stylish and good. One from Denmark. That's a powered one. Uncommon to find powered consumer loudspeakers, but when you power it, then you have even more power, more control over how it's going to perform. I mean, that's just excellent. And here's an example, whether you like the look of it or not. Some people do. I do, actually. I think it's an attractive speaker, but it's a demonstration of what competent engineering can do when combined with good industrial design. You don't have to have a rectangular box to have a good loudspeaker. You can, if you know what you're doing, you can design good sound into almost any shape you like. A few manufacturers have changed how they present specifications. You can go on some of the websites and find spinoramas. Others you find good anechoic data. Either way, you can begin to understand how the speaker might sound. Most of them don't tell you that. For most of them, there's more information on the side of a tire than there is. I love that little comparison because it's absolutely true. Just go to it. Look at this loudspeaker. Sit at a loudspeaker specs. It's pathetic. But production variations remain a problem, and not all products justify the significant cost of repairing or scrapping out of tolerance samples, and not all manufacturers care. So that is a continuing problem in the industry. Again, William Gibson. Thank you. That's it.
I think, that you were the most attentive audience I've ever seen in my entire life. Thank you very much for your patience.
I didn't see anybody fall asleep.
No, nobody, not at all. Absolutely not. Thank you, Floyd, for your insights. Do you want to take some questions? I'm gonna leave
I'll take questions. Sure.
Okay.
Long as
I know there's some questions. Okay, we got a front row question right here.
Yeah.
Thinking back to one of your earlier drawings, graphs there, where you were showing the cues for different resonances and the audibility of those, how would you describe the audibility if those weren't resonances, but in fact dipping below
I'm
nulls?
sorry.
Nulls.
If it's not a peak, but a rather null,
Yeah.
well, the only way that can possibly happen is if there's a narrow band absorber in the space, right?
Is it an audible artifact?
It's less audible than a peak,
Okay.
for sure.
That's
Oh yes,
yeah.
that has been tested way back.
Okay.
Bookline, I think it was. Yeah, and dips are less audible than peaks, and it almost makes sense when you think about it, because in the natural world, dips occur through acoustical interference, and acoustical interference is very position sensitive.
Okay, thank you.
Thanks again for the presentation. One thing that struck me while you were speaking was that mixing technique and convention was developed during a period when loudspeakers were quite poor. So I wonder if you've seen, since the development of these techniques and this new data, that engineers have changed the way that they choose loudspeakers or their mixing techniques.
I don't have enough intimacy with the professional recording industry to answer the question intelligently, really. I follow the forums, and the professional audio forums are still full of folklore. I mean, they still build NS10s and Oratones. They still exist. In fact, there's a company that just produced a modern version of the Oratone 5C, would you believe? As if the world needs that today. The Oratone 5C was a 5.25-inch, $2 paper cone speaker that was used in television sets and table model radios in the 1960s. And somebody put it in a little box and said, if your mix sounds good through that, it's going to sound good through the typical TV set and table radio of that day. Well, that was the 60s. That's a long time ago. But still people use these, and in fact, was it Michael Jackson's famous recording? Yeah, him. Yeah, that's right. He said 80% of that mix was done on an Oratone 5C. And they attribute, the interesting thing is that these characters attribute the success of the recording to the monitor loudspeaker, not to the musician or the music or the musicianship. You know, give me a break. Thank you. Oh, well done.
Somebody pass that up for you.
Oh, excellent. Thank you.
I've got another question right in the middle.
Earlier on in your talk, you talked about mono. And we've had some experience with mono, ranging from using just one channel and losing most of the essence of the music, like the music performance itself just not being complete. But more surprising, we've had a number of experiences where we've summed stereo to mono, and it's been a disaster. There was a point in time when every recording
Would be
console,
mono compatible.
yeah, looked very, very carefully
Yeah.
at
No,
compatibility.
not all stereo recordings mix to mono sensibly, and you can hear the difference. But in these tests, you're not listening for the fidelity of the recording. The recording is just a test signal. It exists only to excite the resonances. And the reason why high Q resonances can be so high before you hear them is because statistically, in order for it to be excited, a note has to hit that frequency exactly and stay there long enough to pump up the energy in the resonance. And that rarely happens. So it's a statistical thing. It's not that the resonances, that high Q resonances are not audible. They're very audible. By pink noise, it's audible. But in music, the probability of it being heard is low because it is so narrow.
I was kind of wondering where you got your mono signal from. That was
Just
sorry. That,
combine them. And the ones that don't work, it's obvious.
yeah, okay.
We'll go this way. Pass it down. See, we're all family here.
Awesome discussion. One of the key points you brought up, though, when doing the comparisons is about loudness equalization. And certainly the whole field of measuring loudness has evolved over time. And over the time that you've been doing all this research, what techniques have you used?
For loudness, to make them equally loud?
Yeah.
Well, in the beginning, when loudspeakers were so
Yeah. Well,
individualistic, it was impossible. You have to do it subjectively. You can't do it by measurement because the spectra of the loudspeakers are so different that you can't match them exactly all the time. You just have to make a first approximation. But it turns out that even the first approximation is good enough to get you on the way. And as the speakers got better and better, then the matching became a technical exercise.
10 points for Finley for muting the coughs, if you've noticed. My favorite microphone is one with a sound operator attached to it.
Yeah, like, I'm sorry.
I got a question on the preference rating for speakers and the bass extension. As you know, passive speakers, it's very difficult to get good bass extension without the drooping response. So during the development of the preference curve, was there any equalization used to, say, maybe equalize all speakers to have the same bass response and then...
No. No, except the one test where I showed you where we had a good, better, and best loudspeaker. They all were driven with the same subwoofer, so the bass was the same. Sorry, I lied the first time.
Another question here.
Just a question regarding all of your investigations and studies over the years. Have you determined what factor materials play in the listening experience?
Well, materials determine whether there will be resonances in transducers and at what frequencies they occur, and that's all. That's all there is to it. I mean, there are materials. Ideally, you want a material that is massless and perfectly stiff, and no resonances and high efficiency. But real materials have some flexibility, and they have some mass, and so it is the skill of the mechanical engineer, the transducer engineer, to massage the shape and material and structure of the diaphragm of the transducer to push the first resonance outside the bandwidth over which it's being used. That's all there is to it. You want it to be pistonic within the bandwidth over which it's used, and when it starts to break up, you shut it off.
Another question in the middle here.
Can you comment on DSP and room correction in cases where there is a physical constraints of moving speakers? So let's say not every time you can move the speakers to wherever you like and optimize the subwoofers. And there are various technologies today that uses DSP or digital DSPs to fix the issues. Can you comment on that?
Trying to understand the question, actually. You say that the subwoofers are at different locations?
So room correction,
Yeah.
DSP technologies, you can't move the speakers physically.
Right.
So there
If
are
you-
technologies that can supposedly fix the issue.
Well, that's what the sound field management did, because you can actually add delays, and you can electronically move the loudspeaker by introducing delays, and that's what it does.
Okay.
Yeah, it's okay.
Okay.
But you need signal processing in the signal in the line level signal. Yeah.
Did you hear that mute? That mute was.
That was good. Well done.
That was a beautiful mute.
My 87-year-old voice is.
No, thank you very much.
Suffering.
Let's just give another round of applause for Floyd. You know, we'd give him an award, but he's already a gold fellow. What's the?
Silver and gold medals.
He's got both silver and
I've had
gold.
them all.
And we've got another gold medal recipient from the AES in the audience here today. And I don't know if anybody else is a fellow of the Audio Engineering Society, but we pride ourselves on having the most distinguished people in the AES here. So it's really, truly a pleasure to have Dr. Floyd Toole here to continue our efforts to bring, you know, this type of information to everyone. So another round of applause for Dr. Toole.
Thank you. Thank you.
I'll do the plug for the book. There's a book.
There's a book.
There's a
There it
book.
is. It
And
exists.
this is the 4th edition.
And there's a hardcover
And there's a
version
hardcover. Don't tell my wife how much that book
from
cost.
some scandalous price.
Yes, it's scandalous. But if you're going to buy seminal texts, they better be hardcover. That's the way I look at it. So our next meeting, I'm sorry for overloading this. Apparently it comes out of a line level and goes into a microphone input. Look at this. Oh, jeez. Our next meeting's on gain staging. I'm joking. I don't know what our next meeting But thank you, everyone, for coming. My name is Anthony. We are at torontoaes.org. You're welcome to, if you're not a member, or if you've been a member and you haven't renewed your membership, please do. In February, we will have our member showcase, where you can present your idea, your concept, your 15 minutes of fame, whatever you want. Please, send us some ideas, participate. That's the only way any of this happens. We're a volunteer organization. So yeah, I believe, is there after drinks? Are we doing after drinks? Three Kings? What is it? Is Three Brewers on, is that Yonge Street? Okay, everybody knows what I'm talking about here. So Three Brewers, if you would like to come join us for an after event beverage, I think some of us will be there. Thank you again. Another round of applause for Dr. Toole.